feel the vibe.
What's up, guys? Welcome back as we continue our discussion on the RF.2 notes, rational exponents. When we left off, we were talking about how rational exponents correspond to radical expressions. And so just as kind of a refresher here, if I'm given an expression and it has a rational exponent, that expression can be rewritten as a root, where the numerator of the expression is the exponent of that, or sorry, the numerator of the exponent is the exponent or the power of that expression, and the denominator of my rational exponent is the index of a root. The order of those two things can be switched around as needed for convenience. In addition to that property, we have been using and reviewing properties of exponents in combination, and so they are displayed here on the screen. We are going to continue to use these as we look at more examples. So our goal here has been to simplify these simplify these expressions, listing our answers in rational exponent form. So here, as I take a look at L, I have 3x to the negative 1/2 times 3 times x to the 1/2 times y to the negative 1/2 divided by 3 and y to the negative 7/4. So what I should look at doing here is starting to combine bases that are the same. My bases would be like the integers would be a base, or x's would be a base, the y's would be a base. So I'm going to go ahead and attack this problem using the properties of exponents that we have here. So essentially what I get is I get 3 times 3 divided by 3. So if I want to think about this as exponents, I get I could rewrite this as, sorry, let me change the size of this font here. I could rewrite this as 3 to the first power times 3 to the first power, which would mean I add their exponents, divided by 3 to the first power, which would mean I subtract its exponents. So you wouldn't necessarily have to show out this work, but this is how we can simplify the integers. Now I have the bases of x, so I have x to the negative 1/2, and that's getting multiplied by 1/2, so I'm going to add those two exponents. So they have the same base, I'm going to add the exponents. Then if I look at the y's, I have y to the negative 1/2, and it is being subtracted by negative 7/4. So, sorry, subtracted by a negative 7/4. So the reason we subtract there is because I'm dividing the bases, so I subtract the exponents. Now if I simplify this, 3 to the 1 plus 1 minus 1 power, so 1 plus 1 would be 2 minus 1 would be 3 to the first power, or just 3. X, I would have negative 1/2 plus 1/2, which would be x to the 0 power. I'll come back to that. Then I would have y to the negative 1/2 minus 7/4. So if you need to, we can definitely do this in the calculator. We can do negative 1/2 minus negative 7/4. And then we're going to go ahead and put that into a fraction. And so y would simplify to 5/4. Now remember, the zero product property tells us that anything to the 0 power is going to be equivalent to 1. So x to the 0 power can just be rewritten as 1. So this would be 3 times 1, so just 3. And then y to the 5/4 power. And so we're going to go ahead and leave that in rational exponent form. Now if you wanted to, yes, you could write this as 3 times the 4th root of y to the 5th, which would simplify to 3 times y times the 4th root of y. So you could simplify that as a radical expression. But for our purposes, we're going to leave this in rational exponential form as 3 times y to the 5/4. Let's go ahead and take a look at another example. Example M. In example M, we have m times m to the negative 7th times n to the 5/3 power. That expression, all of that is going to be taken to the second power. So what I can do is I can simplify inside the parentheses first if I want to, or I can essentially evaluate for the second power here. So I'm going to go ahead and simplify inside the parentheses first. So if I have m to the first power times m to the negative seventh, that would be m to the first minus 2, or plus a negative 2. So I'd add those exponents. And then I'd have n to the 5/3 power. So this would end up being m to the negative first power, which is the same as 1 over m. So I'll go ahead and write this as 1 over m. 1 over m. And then I'd still have n to the 5/3 power here. Now this is all still be taken to the second power. So remember, if I have an expression with an exponent, and I'm taking that to a power, I'm going to multiply my exponents together. So n to the 5/5 taken to the second power would be 5/3 taken to the second power would be n to the 10/3 power. I would also take m to the second power. I'd have m to the second power. And this would be my final answer here. So here we simplified inside the parentheses first by adding together the exponents of m and then realizing m to the negative 1 first power, that's the reciprocal operation, so it would be the same as 1 over m. So this would change n to the 5/3 over m, and then we evaluated that power. Now let's do n a little bit differently. Let's evaluate the power first. It's a similar problem. We have a division inside the parentheses, so I could simplify inside the parentheses if I wanted to. But let me go ahead and just evaluate the power first to show you a different way to do it, but still get to an equivalent expression at the end. So I'm going to evaluate this fourth power, which means I essentially distribute the fourth power to everything. So I would have x to the 1/2 power times 4. So if I take an expression that has a power to a power, I multiply those exponents. I would have y to the negative second power times 4, all over y to the first power times 4, which is just y to the fourth, and then x to the negative 7 over 4 power times 4. Now let's simplify this expression. So this would leave me with x 1 to the 1/2 times 4. 1/2 times 4 is just 2. Y to the negative 2 times 4. Negative 2 times 4 is negative 8. Y to the fourth is still down here. And then x times negative 7 over 4 times 4 would be negative 7. Now I'm going to continue to simplify this. I have a division of common bases. So with the x, if I'm dividing here, if I'm dividing an expression or a base and they have exponents, I'm going to subtract their exponents. So this would be x to the second power minus negative 7, which is the same as 2 plus 7. We'll come back to that. Then I would have y to the negative 8th power minus 4. So I would be subtracting the exponents. Now I can simplify. So x to the 2 minus 7 power would be x to the 9th power. Y to the negative 8 minus 4 would be y to the negative 12th power. And remember that negative is a reciprocal function. So this would be x over 9, x to the 9th over y to the 12th. And this would be our final answer. Now, you could have done that differently. You could have simplified inside the parentheses, and it may have actually been shorter in this case. Probably would have been shorter in this case. So if I would have simplified in the parentheses, I would have taken x to the 1/2 minus the negative 7 over 4, and I would have taken y to the negative 2 minus 1, simplified that, and then distributed that fourth power through. And we're going to see it would be a little bit shorter. So it's probably best to simplify inside parentheses first if you can, just to kind of shorten the number of terms that you have to take another exponent to. Either way, if you've done correctly, you're still going to come up with the same answer. Let's go ahead and take a look at another problem. So in O, there is an order that we need to make sure that we follow here. Notice that the parentheses here in the numerator have a 3/2 power, and what's in the parentheses here have a 1/4 power. If I'm going to simplify, I do need to follow order of operations first. Now, what I did here If I simplify inside parentheses, that's okay. If I simplify with distributing the exponent like we did here, that's still okay. It's not changing the parentheses because it's taking the operation to everything inside the parentheses. I cannot divide first here because that's going to change what's the operation that's occurring in the numerator. So I have to work with the exponents inside the individual parentheses here. So again, if I have a set of exponents, or I have a variable or an expression to a power, and I take that to another power, I'm going to multiply. So this would be x to the 3 times 3 halves power, y to the 2 times 3 halves power, all over x to the negative 1 times 1/4 power, y to the negative 2/3 times 1/4 power. And as we simplify this, I get x to the 9 halves in the numerator times y to the 3rd power. In the denominator, I get x to the negative 1/4, y to the negative 2 over 12, which would be negative 1/6 power. Now I've worked through the exponents in the parentheses, and now I can move on to the division. So when I divide common bases, I subtract their numerators. So x to the 9 halves power minus a negative 1/4, y to the 3rd power minus 1/6. And if we need that help with the subtraction, we can again do that on the calculator. So 9 over 2 minus negative 1 over 4. If I do that in the calculator, it gives me a decimal. I'm going to put that as a fraction. So x to the 19 over 4 power. Then I would have y to the 3 minus 1/6. Sorry, that should be y to the 3 minus negative 1/6. So I forgot that negative down here. Y to the 3 minus negative 1/6 would be y to the 19 over 6 power. And this would be our final answer. Now again, this is in rational exponential form. If I wanted to put this into root form, I could take the 4th root of x to the 19th and the 6th root of y to the 19th. And what I would end up getting here is x to the 4th, 4th root of x to the 3rd, and then I would get y to the 3rd, 6th root of y. Okay, so these are equivalent expressions, but for the right now, we're going to go ahead and stop at the rational exponents. So at this point, we have one problem left. We have p remaining. See if you can complete p, and then check it with what we have on the video. Hopefully you got a chance to pause that video and complete p. Now let's go ahead and take a look at the answer. So if I look at p, I have a parentheses. I could look in that parentheses. There's nothing I could simplify there because I have two different kinds of bases. So in order to use our exponent rules, notice that with the exponent rules, in order to use these, the bases have to be the same for the product, quotient, and the power properties. We've got to be working with a single base. So here, I'm going to go ahead and essentially evaluate for the power first, distributing that power to everything inside the parentheses. In the numerator. So only the numerator is taken to the negative 5/4 power. So this would be the same as x to the negative 1/2 times negative 5/4 y squared, or it's y to the 2nd times negative 5/4. And all of this would still be over x to the 2nd, y to the 1/2. So that negative 5/4 is only distributed to the numerator. As the numerator is in parentheses, that negative 5/4 is pertaining to only those terms. So as I simplify, x to the negative 1/2 times negative 5/4 would be to the 5/8 power. Y squared times negative 5/4 would be y to the negative 5/2 power. Then in the denominator, I'd have x squared and y to the 1/2 still. Now, for the exponents, now that I've simplified the numerators and denominators, I can divide the common bases, which means we subtract. So this would be x to the 5/8 power minus 2, and y to the negative 5/2 power minus 1/2. So this would give me 5/8 minus 2 would be x to the negative 11 over 16 power. Sorry, I had the wrong base there. That should be negative 11 over 8. So negative 11 over 8 power. And then I would have y to the negative 5 halves minus 1 half. So negative 5 halves minus 1 half would be negative 6 halves, which is negative 3. Now, when I generally list things in rational exponential form, I need to get rid of the negatives. So remember, the negative is the reciprocal of these. So I would have 1 over x and 1 over y. So in this case, 1 over x to the 11 over 8 power, y to the 3rd power. And this would be our final result here. So we're working at using a combination of our exponential properties here to simplify these expressions, as well as, if needed, to put them into roots. We could do that here using our combination with root functions and rational exponents. And this is a good place to stop for the RF2 notes. So we have gone through a variety of examples here of how to correspond rational exponents to radical expressions and how to simplify using our property of exponents. At this point, you guys have the skills necessary to complete the homework assignment. Soon we will reconvene in class, give you the opportunity to ask some questions, go over maybe some further examples if needed, and then we will prepare for an assessment. As always, thank you guys for tuning in, and I'll see you soon.